Should restart the proceedings, and we've got Aubrey Truman, and he's going to talk to us about Burger equations and elliptic states, and then a lot more.
Okay, so first of all, I'd like to thank the organisers for inviting me to give a talk at this workshop. I think my talk owes more to Isaac Newton than it does to Kiyoshi Ito, so I'm very pleased to be able to give it in the Isaac Newton Institute. You'll see that as part of my talk, there'll be a number of unsolved open problems in classical mechanics, and what I want to do is to present a new Burgers-Zeldovich model for the condensation of planets out of a protosolar nebula. This problem goes back a long way, of course. My interest in it started about 40 years ago when I went to a talk by Sergio Albaverio, and he was discussing joint work with Raphael Herg-Krohn, in which they were proposing using Nelson stochastic mechanics as a means of explaining some of the features of the solar system. And so it sat on one side for about 20 years. I then gave it to a PhD student, Richard Durran, and we made some progress, and we published one paper on the circular orbits. And then just a few months ago, Richard and I got together with Andrew Neat, and very shortly afterwards, two papers followed. And it's the outcome of those two papers that I want to use in connection with the condensation of planets out of a protosolar nebula. Now, the Burgers-Zeldovich model has been used extensively to determine the distribution of matter in the early history of the universe, and what I want to show you is how just a very elementary approach to this problem can give you a very simple Burgers-Zeldovich model. I will show you the model, the stochastic partial differential equation, and I will then show you what I think are the key ideas to handle this equation. There are two rather beautiful formulae, I think, which originated in my earlier work with Weizhong Zhao, who was over here, by the way. So that's what it's all about. I will probably finish early because I'm afraid I've got to leave immediately after my talk. The forecast for the weather on Sunday is atrocious, and it takes me 2 days to get back home. So I will make a hasty departure, right? Okay, so this is joint work with Andrew Neat. The other person I should mention is Fengyu Wang, who is our new WIMIX professor in Swansea. And you will see that one of the most important results is joint with Fengyu. Fengyu is our Wales Institute of Maths and Computational Sciences professor. Terry is the director, right? So it's very important I mention Fengyu. Okay, so let's tell you about the talk. The beginning of the talk is just a tutorial. I'm going to give you a quick tutorial on Nelson's stochastic mechanics. I'm then going to introduce the quantum elliptic states, and I'm going to talk about the Bohr correspondence limit, classical mechanics, the formation of planetesimals, and a stochastic Burgers equation. Unlike previous Burgers equations, this is a Burgers equation with vorticity, and that's what's new. The dark matter community have been saying that if they want to model dark matter, they need an equation for a pressureless fluid, but with vorticity. And we're talking to Grishuk in Cardiff, who is a member of this dark matter community, with the possibility of applying our equation to dark matter. So let's start off with the tutorial. So let's consider the most elementary setup of all. A unit mass particle diffusing in d dimensions. dx of t is b of x of t, t dt plus epsilon dbt. Then the probability x of t is in some Borel set A, is given by the integral over the density, rho of y of t. And of course, this satisfies the forward Kolmogorov equation here. The operator here, of course, is G star, where G is the generator of the diffusion process. G is epsilon squared over 2 Laplacian plus b dot grad. And we have to give ourselves the density at time 0. Oh, it's back again. Right. Good. Okay, so we want to introduce some dynamics, and of course the sample paths are almost nowhere differentiable with probability 1. So we have to follow Ed Nelson, and we introduce these mean forward and backward derivatives as conditional expectations. So this defines d plus or minus of any function of x of t and t, where x of t is our diffusion process, and these are conditional on being given x at time t. And of course it's well known that the d plus of x of t is what we call the forward drift, b of x of t, t, or b plus of x of t, t. And there's also a backward drift, b minus of x of t, t, which is d minus of x of t, which is the forward drift minus epsilon squared grad of the logarithm of the density. And there are osmotic and current velocities here. The osmotic velocity is u, which is half the difference, and the current velocity, v, is half the sum. Now, we want to introduce dynamics, and we want an analog of Newton's second law of motion, and we have to introduce the so-called stochastic acceleration for our diffusion process. Well, this is what it is, a half d plus d minus d plus acting upon x of t. So this is going to play an important role in what follows. So if you think for a moment about quantum mechanics and the most elementary setup of all, that of a unit mass in state psi t in L2, then you can rewrite the Schrödinger equation in this form. All I've done is take the usual Schrödinger equation and multiply both sides by psi star, the complex conjugate of the wave function. And then, of course, this term here is v mod psi squared, and v is real, and mod psi squared is positive semi-definite. So this is real, this term here. And we can equate real and imaginary parts of this equation. Let's first of all equate imaginary parts, and that eliminates this term. And if you look at the quantum mechanical particle density, which is psi star, then it's easy to derive this continuity equation. Delta rho by delta t plus the divergence of j is naught, where j is this probability current here, h bar over 2i psi star grad psi minus psi grad psi star. H bar, of course, is Planck's constant divided by 2 pi. So if you now assume the wave function can be written as e to the r plus I s, then put epsilon squared equal to h bar and define the drift b to be h bar gradient of r plus s. This is just a logarithmic derivative, essentially, of the wave function. Then if you look at the quantum mechanical particle density, it's psi star psi, so it's e to the 2r with a normalization factor. Well, this satisfies this equation here, which is a forward Kolmogorov equation. That's an elementary exercise. d rho by dt is the divergence of epsilon squared over 2 grad rho minus rho b, where b is this drift. So it looks as though in the Schrödinger equation there might be hidden some diffusion process, and there is indeed, and this is the Nelson diffusion process. You can also calculate the stochastic acceleration in terms of r and s, and that's what this expression is. And we equated the imaginary parts of our Schrödinger equation and got out the forward Kolmogorov equation. We've still got the real parts of that Schrödinger equation to equate. Well, guess what, folks? This is Nelson's discovery. If you equate the real parts of the Schrödinger equation, you have the analog of Newton's second law of motion, namely that the mass times the acceleration is the force. A of x of tt is minus the gradient of v. V is the potential in our Schrödinger equation. So this is quite an intriguing connection, which was discovered by Ed Nelson about 1960. His book, The Dynamical Theories of Brownian Motion, is all about that, and then there's a second volume, Quantum Fluctuations. And he's had a kind of love-hate relationship with this. We sent him our first paper on his birthday, and he wrote me a beautiful email back thanking me for a marvelous birthday present, right? So he isn't totally disenchanted with his ideas on quantum mechanics. Okay, now, of course, we don't want to treat our particles quantum mechanically. If you think about astronomical systems, for the most part, you ought to be able to treat the particles classically. Or maybe you should treat them quantum mechanically. Well, there's a halfway house. We want to treat them semi-classically. And how do you come up with a semi-classical theory? Well, this is well known to physicists. You have to use what's called the Niels Bohr correspondence limit, which was written down in 1927 after a lot of argument with Einstein. So let's look at a stationary state. We're only going to look at Nelson's stochastic mechanics for stationary states. These are the least controversial cases of Nelson's stochastic mechanics. And we're going to take the correspondence limit as h bar, this is epsilon here, tends to 0. But you have to take this limit in a way that means that the eigenvalues, which are the values of the quantum mechanical observables, remain fixed. So you let the quantum numbers tend to infinity, and you let epsilon tend to naught, so that the actual eigenvalues remain of order 1. And they're you believe, Bohr argued that those would be the physically measurable values for those observables, like energy, angular momentum, etc. So it's clear what you have to do. Now, I'm not going to go through it at this point in great detail, but you can do it in general in this setup here. And of course, you want to know what happens to the real and imaginary parts of the Schrödinger equation in the correspondence limit, right? Well, it turns out that you get two very nice results. This is the Nelson-Newton law. This is what it translates to in the correspondence limit. It merely says that the energy of this system is a half times the modulus of the gradient of s squared minus the modulus of the gradient of r squared plus v. Slightly odd. Wouldn't it be so much nicer if this said a plus instead of a minus? Because then it would look like total energy is equal to E. The other part of the equation is just that the gradient of s dot the gradient of r is naught. A very nice identity. So the level surfaces of S and R meet orthogonally. You should be so lucky. Well, how do we look at this equation? We just have to be a little bit brave. What we do is we take some of this minus mod grad R squared term and we put it with V. The person who had this idea a long time ago, he didn't do it in the same way. He had a different idea as to what the correspondence limit was, but we have got, I think, the correct correspondence limit. But Bohm, who was the professor of mathematical physics in Bristol, said we should introduce this Bohm potential, which in our case is minus the modulus of gradient of r squared. And then what this equation says is a half mod grad r squared plus mod grad s squared plus v effective is equal to E. So all that the correspondence limit is doing for us is it's telling us that you shouldn't just work with the physical potential V, you have to also work with the potential of the state, the quantum state of the system minus mod grad r squared. This is the Bohm potential. If you look it up in books in physics, it's not in that form because they have not taken the correspondence limit, but this is the correct correspondence limit. So this then is our limiting Nelson diffusion, and we can see already that Isaac Newton is at work here, because if you look at the drift, B equals gradient of R plus S. If you look at the equation for this expression here, it simply says a half mod B squared plus V effect. The effective potential is equal to E. And it's easy to prove that if you solve this equation with epsilon equal to naught, you actually have a solution of Newton's laws where the potential energy is the effective potential, this guy here. So that's a one-line proof. All you need to notice is that the B is a gradient, right? And do a little bit of calculus. So this begins to look like a reasonable theory. Of course, if you're going to use this equation, you have to start off x at x. Whoops. Hello. What do I do? Touch anything. There's no flashing button. Oh, this one. One green, and it stopped flashing. It should come back, I think. There it is. There it is. Sorry. Okay. So you have to start it off with the right momentum. And that, of course, is given by the Nelson diffusion equation, right, when you put the time equal to 0. Okay. Well, already we see a Burgers equation here. And what you have to do is you put S twiddles equal to R of x plus S of x minus ET. And then B, which doesn't depend upon the time, is the gradient of S twiddles, which is grad of R plus S. And then because of the result I showed you a second ago, we know that S satisfies this Hamilton-Jacobi equation, where the V is the effective potential. Well, knowing that you've got a Hamilton-Jacobi equation, those of you who've worked in this subject will realize that if you take the gradient of that, out pops a Burgers equation. So we can see Burgers is already here in this correspondence limit. And you just can't avoid Burgers if you're writing down correspondence limits of quantum mechanics. Now, we want to look at this problem for a specific physical system, the physical system in which I have a Hamiltonian corresponding to some massive gravitating object at the origin with a Coulomb potential. Mu g is just one symbol. We've got so many mu's in this subject, you run out of letters of the alphabet. So this is the Hamiltonian. This is h bar squared. And if you look at the usual eigenfunctions of this Hamiltonian, they're well known to all the physicists. They're labeled by 3 numbers, psi n l m. N is the principal quantum number, L is the total orbital angular momentum, and m is called the magnetic quantum number. And h psi is en psi, where en is this nth eigenvalue of the system. This is essentially Balmer's formula for those of you who know physics. And n is a natural number. L and m are in z, where L is greater than equal to 0 and less than equal to n minus 1. And m is restricted to be greater than equal to minus L and less than or equal to L. This gives a complete orthonormal system of eigenfunctions for this problem. Now, of course, Newton knew all about energy. He also knew all about angular momentum. And it turns out that L squared acting on psi NLM is just epsilon to the 4th times LL plus 1. And L3 acting on psi NLM is epsilon squared times m, psi NLM. What Newton didn't know about is this vector here. This is the so-called Hamilton-Lentz Runge vector. It was first written down, I think, by Lentz, and I think he was a student of Ising, right? And the point is that the angular momentum vector L and A are the generators of the dynamical symmetry group for this Hamiltonian. The dynamical symmetry group is just SO4. This was discovered by Wolfgang Pauli in 1926. And we're going to need this A, right? Physically, what it corresponds to in the Kepler problem is it's a vector pointing in the direction of the major axis of the orbit, and its length is essentially the eccentricity. It's a beautiful vector, and it's constant classically, right? So, of course, it should be rather nice quantum mechanically. If you want to form now the Kepler elliptical state, we start off with the circular state. This is a state in which the particles are concentrated on a circle in the z equals 0 plane. And if you fool around with this, you'll very quickly discover the only candidate for that is psi n. You put L equal to n minus 1, and you put m equal to n minus 1. And in this state, if you calculate the expectation values of the vector A, you get 0, and of L1 and L2, you get 0. But for L3, this is the angular momentum about the normal to the plane of the motion, you get epsilon squared n minus 1. And here's a plot of the particle density in the z equals 0 plane. And you can see it's nicely circular. Okay. We want the elliptic state. And this took a long time for physicists to find. It wasn't actually found until 1991. And the way you construct this is you take the second component of A, you exponentiate it, and you hit the circular orbit with it, right? And then it's easy to prove, this just uses Pauli's solution of the hydrogen atom, that the expectation value of A1 is epsilon squared n minus 1 sine theta. The expectation value of L3 is epsilon squared n minus 1 cos theta. And of course, because cos squared plus sine squared is 1, it turns out that sine of theta has to be the eccentricity of this orbit. Think of the classical relation between eccentricity and E, the well-known classical identity. E is the square root of 1 plus twice L squared E over mu G squared. This is the quantum mechanical analog of that. And it's telling you that this is indeed an elliptical state. Its eccentricity is sine theta. And it's in the plane z equals 0. The semi-major axis is n squared epsilon to the fourth over mu G. Lehner, Deland, and Gay worked out the exact expression for this in Cartesian coordinates. And here it is. This was in 1991. And it involves a Laguerre polynomial. There's a simple exponential, and then this Laguerre polynomial. It also involves this rather bizarre variable, nu. This crops up everywhere. There ought to be some simple geometrical interpretation of it. If you deal with the two-dimensional problem, there is, but I cannot find what it means in 3 dimensions geometrically. There's a problem, first PhD problem, right? It's just a piece of geometry, right? Somehow it's related to these ellipses, right? In the plane, I won't show you now, I'll show you later. Okay, so this is an explicit formula now for our elliptical state. And of course, what we need to do is to look at its Nelson diffusion. Here it is. And of course, you've got to take the logarithmic derivative to find the R and S functions before we can write down the drift. And you get these horrible quotients. This is L prime n minus 1 n nu over ln minus 1 n nu, the same here. And you've got to take the limit, the Bohr correspondence limit, as n goes towards infinity in here. And it's not very nice. Well, that held us up for some time. But this is a simulation of what the orbit looks like. If you write down the Nelson diffusion, you simulate it numerically, you do indeed get convergence to ellipses. But we want to take the limit as n goes towards infinity, epsilon going to 0. And you need to work out the limit of that quotient. Well, that's done here. This is the key lemma. It turns out that this quotient in the correspondence limit has this nice limiting value, where nu is that horrible variable I showed you a minute ago, right? That then gives you, of course, the Nelson drift in the correspondence limit. And that's what's written out here. And it's a nice expression, right? Just involves this nu and some relatively simple vectors. E is the eccentricity of the orbit, modulus of sine theta. And here's nu. Okay. The limiting wave function is here. Remember, this will not satisfy a Schrödinger equation exactly because we've taken a limit, right? But there are still things you can do with this, right? So what is this limiting diffusion now? Well, of course, now we know what the limit of the quotient is. We can work it out explicitly, and here it is. Whoops. Gosh, that went a bit fast, didn't it? This is the expression in Cartesian coordinates for the drift. Second PhD problem can you prove pathwise uniqueness for the Nelson diffusion with this drift? The drift looks extremely simple, apart from the fact you've got these alpha and betas here. Alpha, beta, alpha, beta, alpha, beta. And alpha plus I beta is the square root of 1 minus 4 over nu, bottom of the slide, where nu is that weird variable. It looks like you can probably prove it in 2 dimensions. I don't know how to prove it in 3 dimensions. Okay. So here's alpha and beta. You can work them out explicitly. And they're nested radicals. And of course, they have singularities. They have jump discontinuities. That's the simulation. It looks even more elliptical now you've taken the semi-classical limit. These are the singularities. And this purple surface here, on this surface, B as a finite jump discontinuity, but blows up on this edge. That's the source of all our difficulty. Okay. So for the exact diffusion, we know what the invariant measure is because quantum mechanics has told us that, right? It's e to the 2r epsilon n of x, right? And what we want to know is what it is for this limiting case. Well, we have to make an ansatz here. You very quickly realize that it has to have e to the 2r epsilon of x as the dominating factor. And then there's a t of x here, which you have to assume is positive, and you also have to assume has an asymptotic series in epsilon. And you need all sorts of smoothness conditions and boundiness, as you'll see in a second. That's the limiting density. And the big problem, of course, is what happens for the large time limit of this diffusion process. If it's going to be any use at all, it has to converge to the elliptical orbit of Kepler. Well, does it or does it not? If you don't have pathwise uniqueness, there's not a lot you can do except in 2 dimensions. But it turns out that there's a spectral gap for the generator of this Kepler diffusion. This is work which we did with Fengyu Wang. Here he is. Fengyu Wang, our WIMIX professor. And he has a beautiful book, which I'll show you in the references. Beautiful book. Okay, so how do you prove this? Maybe I don't have time. I will just say a little bit about it, right? So we assume the invariant measures of this form here, where V epsilon is 2 R epsilon plus log T, and you need to establish a Poincare inequality for f in C naught 1 of R3, satisfying the integral of f d pi epsilon is naught. And this is the Poincare inequality you have to prove. And this took us quite a long time. I mean, the basic assumption is this one here. The modulus of the gradient of the log of t of x has to be less than a constant for sufficiently large mod x. And remember, we've got this singularity. That may not be true. So this does work on a wing and a prayer, right? Anyway, this is the details of the proof. I don't think I've got time to go through it. I'll come back at the end, but this is, honestly, this is a beautiful proof. I take no credit for it, right? And it's in our second paper, the last 4 pages. It took a lot of blood, sweat, and tears, right? So you get this second Poincare inequality. You combine the lot with Cheeger's inequality, and you end up here with the spectral gap lambda 1 greater than this quantity here. Okay, so we've now got a dynamical system when we put epsilon equal to naught. Of course, if you avoid the singularity, we can prove that you get this nice uniform convergence here using Wenzel and Friedlin. And so if you understand the x naught system, you've got some hold over what's happening with the Nelson diffusion. This is the conditional expectation, assuming you avoid the singularity. And as I said, Newton occurs on every 5th slide. You have this nice set of Newtonian mechanics. You say, well, this is all well and good, but what is the gradient of R? This is the Bohmian potential. This is the gravitational potential, this the Bohmian potential. These are the simulations. This is the singularity of the drift. It's also, of course, a singularity of this potential. You don't gain anything, right? But it's nice to see Newton sitting there. Okay, so this is the gradient of r. If you square this length, work out the length of this vector, you've actually got the Bohm potential for all of these elliptical orbits with a given eccentricity and a given semilatus rectum, right? Some level surfaces here, which Andrew has computed for us. Notice the level surfaces of R are just elliptical donuts following the Kepler orbit. R is a maximum on the Kepler ellipse. And as you change the value of the constant, all that happens, this becomes a punctured sphere. And the level surfaces of S are drawn here. They just drive the particle around this elliptical orbit. But you've still got always to live with this singularity. Well, there are lots of results in our paper, our first paper, about the dynamical system with epsilon equals naught. I won't bore you with them, right? The main one is that this orbit is orbitally asymptotically stable, an orbitally asymptotically stable limit cycle. And that Kepler's laws hold for this limiting diffusion. So the actual particle approaches the Kepler ellipse and eventually describes the Kepler ellipse in a way consistent with Kepler's laws. Okay. This is just telling you that the invariant measure is concentrated on the Kepler ellipse. And this is the Bohmian potential. What I'm doing here is I'm making propaganda for the Bohmian potential. Because you'll see this drives everything. Okay. This is the force field. If you look carefully at this, you'll see we don't understand it. There's a circle here, right? We don't understand where it comes from. This is the Kepler ellipse. And here there's a clear circle. Any PhD student might want to look at that. This is just a blown up version of this center portion, the diagram. This is the velocity field. This is some fancy pants analog of the fluid motion, the Burgers fluid motion. It's on Mathematica, right? Didn't work very well. Okay, so what about the Burgers equation? Well, the first thing to say is that we have the limiting wave function here, and we have a Nelson-Newton law. Even though this doesn't satisfy a Schrödinger equation, it still obeys a Nelson-Newton law if you assume the density is given by this e to the 2r epsilon over epsilon squared. So again, you're reminded that there's a Bohmian potential coming into play here. If this was just the usual Nelson-Newton law, you wouldn't have this epsilon squared term, right? This is the gravitational potential, and this is the Bohmian potential. Now, I want to show you where the action is and where the stochastic partial differential equations come from in this setup. So I want you to imagine that you've got a swirling cloud of, shall we say, quantum particles, and that an appreciable fraction of these are in the state corresponding to the Keplerian orbit, right? And what we're going to do is we're going to model their motion with Nelson stochastic mechanics. So these Nelson gas particles, right, are in this atomic elliptic state, and they're going to converge to this tubular neighborhood of the Kepler ellipse. Our expression for the invariant measure has that feature, and the limit as epsilon goes to naught. And I want you to imagine that they form a train of planetesimals orbiting around the Kepler ellipse according to Kepler's laws. I mean, they all pile into this elliptical tube. You have no way of stopping that, right? And what I want you to assume is that you've got an incoming let's do a very simple model. It's a completely trivial model. You'll see you can make it more sophisticated, but here just let's have a look at an incoming gas particle, Nelson gas particle, of mass m of t, and a classical orbiting planetesimal of mass big M, right? And little m is very much less than big M, right? and let them collide according to Newton, right? And what you see happening, this is just the condition of momentum conservation. The planetesimal is moving classically, so grad r is naught. And this is the momentum before the collision. This is the gas particle before the collision. And this is the planetesimal before the collision. This is after, and this is after. Write down the equation for momentum conservation. We know the form of the momentum has to be a linear combination of grad s plus grad r and grad s minus grad r. Remember, grad s dot grad r is naught. And we have p plus q has to be 1. And this is the equation for m and delta m and p minus q. So this tells you straight away what q has to be. It has to be minus delta m over 2m. Remember, p plus q is 1. And so, as a result of one of these collisions, the velocity field of the gas in this tubular region will go from grad s plus grad r to delta m over m grad r. So the velocity v of the gas particle after t seconds will look like this. And what assumptions are we going to make about this process, log of m of naught over m of t? Well, we should assume it's infinitely divisible. And because I haven't got any time, we're going to assume that it's got no jumps, right? But here's another PhD problem, right? So m of t is then just geometric Brownian motion. We need some Brownian motion to drive the whole thing. But Nelson gave us such a Brownian motion. Which one-dimensional component of it do you want? It's the one in the direction of the relative motion. So I would argue that the physics forces you to take this as your m of t. There are only two free parameters, mu naught and sigma naught. Of course, you can make the model more sophisticated by assuming there are ni particles of mass mi of t with different mu's and different sigmas. And then you end up with the same equation, but mu naught is this sum and sigma naught is this sum. But why is this interesting? Well, it's interesting to me at least because there is still a Hamilton-Jacobi equation here. And the important feature is, the new feature of this, is the Hamilton-Jacobi equation has included in it a vector potential. Okay? For those of you who did physics, you will know that such things occur in electromagnetism. And it occurs here too. The S-Twiddles function, this is going to produce in a minute, you'll see, the velocity field in the tubular region. And it satisfies this equation. There's a lot of potentials here. One is the gravitational potential, the other is the Bohmian potential. And then you have the potential coming from the collisions, there and there. But A is very simple. A is just the vector potential, and it's R gradient of the log of m of naught over m of t. Remember, this will depend upon position, space dependent, because of the presence of the Nelson noise in the direction of the relative motion. So this is not 0. A is not 0, right? So I argue that this is the stochastic Hamilton-Jacobi equation for the particles in the gas in this tubular region where all the collisions are occurring. The collision potentials are here. Don't worry too much about them, but I've written them out explicitly. And of course, we have an explicit solution of this, right? You usually start with the equation and find the solution. We started with the solution and found the equation, right? It's a cop-out, right? I believe it's the correct solution. I believe it's the correct equation. Well, the velocity field is grad s minus A. A is our vector potential, which is R gradient of the log of m of naught over m of t. And the stochastic Burgers equation, the game is you write out your Hamilton-Jacobi equation, and then you take the gradient, and you do the vector calculus, and here's the Burgers equation. And of course, you've got vorticity here. You've got the curl of V, right? You don't usually have any, curl of V is usually naught. Here, you can see that curl of V So these collisions, curl of the velocity field here, usually called omega in most fluid dynamics books, is actually minus the curl of my vector potential, and the vector potential A is R gradient of the logarithm of m of naught over m of t. And you're going to get these tiny vortices forming in this tube, right? If you believe in Newton's law of momentum conservation. So this is the Burgers equation. The generic gas particle has velocity field v, and we have an explicit solution. Of course, we also need to add viscosity, right? We've taken the limit of zero viscosity, and this is the hard thing. You've got to add in some mu Laplacian of v, and mu is a function of epsilon. Well, by luck or by chance, I don't know. Somebody loves me, I guess. Turns out we've been looking at this equation, or equations very like it, for about the last 5 years, right? So, first of all, I read an article in the Sunday Times about 2 years ago, before we did this, that said that the explanation for why we have two kinds of planets, terrestrial planets and gas giants, was that when the planets were being formed, behind each planet there was a train of vortices. And I couldn't see how to produce this train of vortices until I did this little piece of analysis here. But it seems to me that already in this model, you have an arc-sine law for the distribution of masses of the planetesimals. This is only the early history of the planets. It's not to do with the planets themselves. It's the planetesimals, right? So while this gas is going into the tubular region. Well, if you do the calculation, this is now only for small eccentricity. So these are for the orbits which are very nearly circular, right? The important quantity is m gas over the volume of the tube, right? This is the density at time zero of the particles in the gas in the tubular region. And there are two times. There's a classical time scale there, and this is a quantum mechanical time scale. E is the eccentricity. Our results work for naught less than E less than 1. They don't actually work for the circular orbit. But this is the leading behavior that one gets for rho p of t. W is just a BMR process. And then asymptotically, you have this result here, where A naught of t is the radius of the planetesimal. And there is indeed an arc-sine law. This is just because you have a Brownian motion, right? And Andrew did some simulations, and it actually is. So what it means is that very massive planetesimals are likely, and very light ones, but intermediate mass planetesimals are not. That's what this slide says. Okay, so what can we say about our stochastic partial differential equation? Well, as I said, we'd actually been working on this for several years, maybe 2 or 3 years, not 5. I don't know, maybe. It's certainly in some of my early notes 5 years ago, right? So how do we handle it? Let's take a model equation. I'm not at this stage going to let A be random, the vector field, right? I'm going to make div A equal to naught. There's gauge invariance here, right? So you can do all sorts of weird and wonderful things with div A and work in different gauges. I'm going to assume that V is twice continuously differentiable, and K here carries the noise, so this is like the collision potential, and this is the actual equation that we want to look at. And it's not very nice, is it, right? It's very like what we had before, except that we've got this horrible term, and we've got this vector potential, of course. And how do you handle this? We've also got the initial condition here. Because, of course, what we do, we use the old standard trick.
In this equation is given, yeah?
Yep,
So
yep.
So unknown is just V.
Yep, exactly. Yes, thank you. Yep. So we make a hot-cold transformation. So what's the corresponding heat equation? Well, it's not half bad. Here it is. We've got some noise here. And we give ourselves some initial conditions. If you look at our earlier work on the ordinary Burgers equation, you'll see this initial condition is all important for getting the right physical initial condition. And then you have this, I think, pretty Feynman-Katz formula. So this gives me a nice Feynman-Katz formula. This term here is the noisy guy. It's like the term one gets. Notice it's T minus S, by the way. T minus S, right? Not T, not S, right? It's T minus S. I mean, the way you obtain this, of course, is you let time be an extra space dimension and write down the usual Feynman-Katz formula and work away, and this drops out. And the xt of S is this. So this term here only incorporates the A, the vector potential A. So, I mean, this is quite obvious. You would have written this down anyway, I guess. I hope you wouldn't have written down the next thing. So, of course, to make progress with this, some of you will know you have to introduce a stochastic flow map. Here it is. This is like the classical mechanics for this problem, but it's classical mechanics with noise because of this dWs here. And of course, we've also got a vector potential. But this term and this term are just Lorentz force terms, right? If you think back to electromagnetism, they're just Lorentz forces, right? And d phi s is phi s dot ds. These are the initial conditions. And of course, you can prove that phi t is a random diffeomorphism up to the caustic time t of omega, which is positive, right? We had our own version of this, and it turns out it's also in Kunita's book, right? So before the caustic time, that's one of the things you'd be interested in. Then you would use your random diffeomorphism to define the classical mechanical action. That's all this is, right? This is the kinetic energy. This is the initial value of the Hamilton-Jacobi function. And this is the vector potential term. Think of electromagnetism, right? This is the electric potential, and this is the noise. And of course, you will know by now, those of you who worked on this, that the important object is not S, but S of phi t to the minus 1 of x of t. This is the one that satisfies our Hamilton-Jacobi equation. So the results exactly similar to this in Kunita with these assumptions. I mean, I wrote out the assumptions. Basically, you want A to be in C naught to infinity. If you want easy proofs, right? You want life to be easy, right? And you want V to be twice continuously differentiable, right? You'll see later you need to assume that the second order partial derivatives are bounded, but we're not going to do that today. So you get the usual equation here for the time evolution of the random diffeomorphism, right? You think about Abraham and Marsden. This is just a rewrite of that when you've got a vector potential as well as a scalar potential. And S twiddle satisfies this Hamilton-Jacobi equation. This is the key. This is what I learned with Weizhong Zhao, right? That everything comes from the Hamilton-Jacobi equation. This is the important equation. It's not the Burgers equation, it's not the heat equation, it's this guy, right? And of course, this determinant satisfies the continuity equation. Again, as in Abraham and Marsden, right? So what about the Hamilton-Jacobi theory? So far, we only had a Guzanov-Cameron-Martin formula corresponding to the vector potential term. But we've also got our S-twiddles solution of the Hamilton-Jacobi equation. So surely we should incorporate that, right? That's the natural thing to do because V is grad S minus A, right? So that's what the physics tells you. So you define this X-twiddles X of T of S by this expression. And S-twiddles is S of phi t to the minus 1 of x naught of t. And then you have this, I think, beautiful expression for the solution of the heat equation. Just so simple, this formula, right? This is the Laplacian of S twiddles. The only thing to be aware of is that it's T minus S here, right? T naught's the initial condition. And of course, what you want to know is what is the actual solution of the Burgers equation. And as with the case without the vector potential, with Wei-Zhong we established some quite nice results for the asymptotic series, and they carry over to this new situation when you have a vector potential. So this is the Hamilton-Jacobi equation with viscosity. Okay? We look for an asymptotic series, and as we discovered with Wei-Zhong, we have the iterated continuity equations, Hamilton-Jacobi continuity equations. This time we've got a vector potential term in. And we can solve these explicitly, just as we did with Wei-Zhong. And you then obtain an even nicer formula for the solution of the heat equation, just here. Here I'm taking the Gazanov-Cameron-Martin formula, corresponding to taking the first m terms of the solution to the Hamilton-Jacobi equation, the asymptotic series. These are mu to the 2j grad Sj. This is the best you can do up to order 2n, right? And you get this beautiful formula, well, pretty formula, right, for the solution of the heat equation. And of course, you get a corresponding result for Burgers. And the point is that you can now set about developing all the results that we had for the traditional Burgers equation in this new setup. And so far, everything we've tried to prove has been easy to prove, right? I'm not saying that there will all, I mean, all the results about Maxwell sets, about caustics, etc., etc., etc. So I will stop there. Thank you for your attention. Right?
Are there any questions or comments?
You had some condition on existing flow of diffeomorphism, which were quite classical in a sense.
Yeah.
And Franco spoke, I don't know, about quite weak condition on flow. Do you think there could be some interaction between?
Definitely. I mean, my private life is very complicated at the moment. One of the things I wanted to do this week was to talk to Franco, right? I'm sure these can be improved. It was a cop-out. I took the easy set of conditions. Yeah, but that's right. Yeah. You have to have the stochastic flow. That's right.
Well, let's thank Professor Truman again.